In this video, I'll be using herding to solve an aspect of Brexit. On the 23rd of June 2016, the British public voted to leave the EU and are set to now withdraw from the EU on the 29th of March 2019. The financial services sector in Britain is very large. In 2017, it contributed to 190 billion of UK GDP, which is around 6.5% of total economic output. Herding is the concept of not following your own private information and following the public information of others available to you through their own actions. For example, when choosing a restaurant, one may want to go to the one with more people in. This can lead to the herd behaviour by using information contained by others' decisions. This creates what is called a herd externality, which is a negative externality on the rest of the population N. There is a population of N agents who are aiming to maximise the same risk-neutral utility function. These agents then take their decisions in a fixed order. Everyone that follows knows that decisions made by previous people and their private information and the signal they received is correct with probability P. Everyone is rational, leading to a Bayesian-Nash equilibrium, but due to the herd externality of ignoring one's private information, this is an inefficient equilibrium. For Brexit, there is a strong belief that the banks will relocate outside of the UK, with over one-third of financial institutions that say they're considering moving. Therefore, I will follow the common belief that financial institutions will relocate to remain within the EU, notably Frankfurt, with the highest number of banks saying they are considering Frankfurt, including JP Morgan and Goldman Sachs. Furthermore, a notable economist has said Frankfurt is the main area of choice for banks, thus creating the herding problem, as it is not known whether the best choice will be to remain in the UK or relocate to Frankfurt. I will create the assumption that the banks will either move to Frankfurt or remain in the UK, and it is currently not public knowledge which is better. There are N exogenously ordered agents in a sequence representing the banks. The decision to move to Frankfurt is represented by F, and to remain in the UK is R. The cost of moving is 0.5, and the payoff from the move has a prior probability of 0.5 of returning 0 or 1. On screen you can see the probability of the outcomes, in that the probability the signal agent I receives is true is between 0.5 and 1. The probability is false is between 0 and 0.5, or 1 minus p. Also, when making a decision, agents can see the history of previous agents' decisions from agent 1 up until the previous agent, with AI being F or L. This is then used to form the information set, which contains both public and private information. If the signal agent 1 receives is that the payoff to move to Frankfurt is high, he will choose to move. Likewise, if the payoff is low, he will choose to remain in the UK. Agent 2 is then able to use this to create the information set I2. If X2 is H and A1 is F, both these signals support each other, and Agent 2 will also decide to choose option F. This is the same for the opposite of A1 equals R and X2 equals L. However, if A1 is F and X2 is L, or A1 is R and X2 is H, then these are conflicted signals, and Agent 2 will choose F or R with a probability of 0.5. Banerjee makes the assumption that if an agent is indifferent between two signals, they will follow their own signal, meaning a cascade would be avoided. This is supported by Anderson and Holt, who found agents will slightly favour their own signal. Here there is a graphical representation of the problem. Agent 1 will follow their signal as there is no other public information. In the cases the two agents make the same decision, then a cascade will ensue. A cascade will happen when all subsequent agents decide to ignore their own private information and follow the herd behaviour. The initiator of the cascade is the agent whose decision makes all of the following agents follow the rationale of the herd, which traps the following person in the cascade, with the herd externality increasing each time. In 4 of the cases in the previous graph, agent 3 will be trapped in the cascade, with H2 either being FF or RR. However, if agent 2 gets a different signal to A1 and decides to follow his signal, agent 3 will be in the same position as agent 1, with the two pieces of public information effectively cancelling each other out. One can use Bayes' theorem to work out the conditional probability of an agent taking an action based on their private information given the public information available. This is by incorporating the probability of a previous event X, the precision of his private information, and known public information Y, with X and Y not being independent. A equals 0 would be remaining in the UK, and A equals 1 would be moving to Frankfurt. So they can either choose A equals 0 or 1. Xi will denote they have chosen A equals 1 based on their private signal, and Y will denote the decision was based on the public information, with the probability of each event occurring being shown on screen. Py being the probability of being guided by public information. The probability of Xi given Y is the probability of choosing to move to Frankfurt based on one's private information given the public information available. Agent 1 will follow his private information A equals 1 with a probability of 0.6, and the public information suggests to remain in the UK with P y given x of 0.48. Using Bayes' theorem, it is clear that private information will be the determining factor in moving to Frankfurt. This also makes the new public information probability now 0.58. For Agent 2, if one assumes the precision of moving to Frankfurt is 0.45, meaning if Agent 2 was solely considering his private information, he would remain in the UK. However, Bayes' theorem shows Agent 2 will exhibit herd behaviour by following the public information. This example would not work if there was no low enough precision to act A equals 1, but does show how individuals disregard their private information and follow herd behaviour.